Good evening, my YouTube viewers. It is Crystal here. I'm just here because I want to give you a code review. I'm giving you a code review on the Kaggle competition U.S. patent phrase-to-phrase matching, and I'm going to use it says BART on it, but I'm not sure that I use BART. I used a pre-trained model, but I'm not sure that it's BART, even though it says it's BART, but it was a pre-trained model. And basically, what happens is I was not able to submit my predictions to Kaggle, and the reason why is because I had to have the internet turned off, and the only way that you can get this pre-trained model is for the internet to be turned on. They did have the facility to use pre-trained models with the internet turned off, but that was using PyTorch. And I'm not using PyTorch in this instance, I'm using TensorFlow. I have studied PyTorch in the past, but I am studying TensorFlow now. And so I did actually send Kaggle a message on their discussion questions, asking them if they have the ability to use TFAutoModel with the internet turned off with TensorFlow, but so far nobody has responded to my question, and until somebody responds to my question, I won't be able to use any pre-trained models. And unfortunately, I don't know enough to do a recurrent neural network with two inputs. I'll have to see if I can figure out how to do that, see if I can find some code that I can study how to do that. But for the time being, I'll show you how to use this pre-trained model with the internet turned on, which I cannot submit to Kaggle because the internet has to be turned off for me to submit it to Kaggle. Which is a shame, really. It's a shame because you can do it with PyTorch, but you should be able to do it with TensorFlow. So we're using the competition question, U.S. patent phrase-to-phrase matching. And this is the Jupyter notebook that I made. I did it in Kaggle, and it's in the repository of that competition question. But what I will do is I will make a copy of the link to the Jupyter notebook, and I will leave it in the description box down below, so that will enable you to look at the code if you want to look at the code. So the first thing we're going to do is we're going to look at the problem statement. It said, in this data set, you are presented with pairs of phrases, an anchor and a target phrase, and asked to rate how similar they are on a scale from 0, not similar at all, to 1, identical in meaning. The scores are in the 0 to 1 range with increments of 0.25 with the following meanings. 1.0 is very close match. This is typically an exact match, except possibly for differences in conjugation, quantity, singular versus plural, and addition or removal of stop words, e.g. the and or. 0.75 is close synonym, e.g. mobile phone versus cell phone. This also includes abbreviations, e.g. TCP, transmission control protocol. 0.5 is synonyms which don't have the same meaning, same function, same priorities. This includes broad, narrow, hyponym, and narrow, broad, hyponym matches. 0.25, somewhat related, e.g. the two phrases are in the same high-level domain but are not synonyms. This also includes antonyms. And 0.0 is unrelated. So that's your problem statement. And what that does is that tells you how you have to make predictions on the label. So the next thing we're going to do is, after we have created our Jupyter notebook and have read the problem statement, we're going to import the libraries. So the first set of libraries that we're going to import is import NumPy as NP, which that creates your NumPy arrays, and it also carries out numeric computations. We're going to import pandas as PD, so that creates your data frames and your series, and it also performs data processing. We're going to import OS, which is your operating system. We're going to import matplotlib.pyplot as PLT, which is your data visualization. And we're going to import Seaborn as SNS, which is also data visualization, but it has a statistical component to it. And then after we have imported the libraries, we're going to use OS to get the files. And we've got 3 CSV files that we're going to use, which are train, test, and sample submission. And you don't have to worry about setup environment. I was trying to set up an environment so I could get it to work with the internet off, but I didn't get to do that. So setup environment is just something that I forgot to remove. And we're going to read the files. We're going to use pandas to read the files. So train equals pd.readcsv, and it gives you the URL to the train file. Test is exactly the same, but it's going to be test CSV, and submission is going to be the same, except it's going to be sample submission CSV. So we look at the train file. You've got your ID, your anchor, your target, your context, and your score. And so we've got the score is our label, and it's going to be what we're going to predict on in the test file. So we check train info, so they're all objects except the score, which is float. We're going to check train, check for any null values. We don't have any null values, so fortunately we don't have anything that we have to deal with regard to the null values. Now we're going to check the test file. You have ID, anchor, target, and context. And you have only 36 rows of data for your test file. And then we check submission. And submission, you're going to have an ID and your score. So the next thing we're going to do is we're going to analyze the train file. And so we're going to analyze the score. So you can see how many we've got: 0, 0.25, 0.5, 0.75, and 1. So you can see how many examples you have of each floating point number. And now we do a value counts on that. And again, you can see numerically how many examples we have of each floating point number. We want to see how many classes we have in the label. So numClass equals train score dot in unique. So that tells you how many classes you have. And then now what we're doing is we're checking the context. And this is the number of examples you have of each context. And this, you can see, you've got a lot of values for each context. And we check the unique values of the context, and you have 106 unique values in the context. And now what we're going to do is we're going to use sklearn. We're going to use their label encoder to encode the score. So instead of, because the reason why is because if you don't encode the score, then you might have floating point values that are different from 0, 0.25, 0.5, 0.75, and 1. So what we do is we put it on the label encoder, and then what the label encoder does is it assigns each number a number between 0 and 4. And then so there we go, have the score label encoded now. So you see it's no longer a floating point number, but now it's an integer. And at the end of the program, we're going to have to reverse what we have done with the label encoder. So you need to remember that. But we're going to reverse what we did with the label encoder, but let me just check that. Yeah, I reversed it all. Fortunately, I reversed it all. Now what we're going to do is we're going to go into TensorFlow, and we're going to be creating the neural network in TensorFlow. So we're going to import TensorFlow as TF from TensorFlow import Keras, and then we're going to print the version of TensorFlow that we're going to be using. So we're on version 2.11, and you have to remember that TensorFlow goes through lots of changes. And now what we're going to do is we're going to import transformers. From transformers, import TFAutoModel and auto tokenizer. And then we check the version of transformers as well. And so that's going to be 4.27.4. And I should have said print transformers.version, but I didn't do it. And the thing is that it takes such a long time to train this data that I'm probably not going to go back and do it. Not unless I want to do some more work on it. But the thing is for me to use the GPU, I only get 30 hours of GPU time a week. And I already received a message saying that I had used up most of my GPU time. So because I'm using it on the GPU, I can't go in and make silly changes to it. And now what we're going to do is we're going to prepare the data. And the thing is, if I was using PyTorch, then I would be able to upload the URL to the PyTorch models, and I would be able to do all this offline. But because I'm using TensorFlow, I can't do it offline. And I have actually put a question in the discussion box asking how do you get to do it offline with TensorFlow, and I just have to wait for someone to come answer my question if they ever do, because I've looked at the other questions that I have asked and nobody has responded to them. And this is an old competition question, so I really don't think anybody's going to be going through and answering questions if I put a question in the discussion in this particular competition question. So model path or name equals BERT large and uncased, which is what I'm trying to use. Model equals TFAutoModel dot from pre-trained model path or name. Tokenizer equals auto tokenizer from pre-trained model path or name. Print model. So now we've got our model, and so the next thing we're going to do is we're going to set up the function to actually encode a sentence. So def encode sentence s, tokens equals list tokenizer dot tokenize s, tokens dot append scp, return tokenizer, convert tokens to IDS tokens. So we encode the sentence. Machine learning is great, and you can see that we get a numerical output whenever we encode the sentence. And so now what we do is we set up the BERT encoder, and we're going to use the anchor, the target, and the tokenizer. So num examples equals len target. Sentence 1 equals tf.ragged.context encode sentence s for s in NP array anchor. Sentence 2 equals tf.ragged constants encode sentence s for s in NP array target. CLS equals tokenizer.convert tokens to IDS. Then CLS sentence.shape, sentence1.shape0, input word IDS equals TF.concat, CLS, sentence1, sentence2, axis equals -1. So input mask equals TF.ones like input word to sensor, CLS equals TF zeros like CLS, type S1 equals TF dot zeros like sentence 1, type S2 equals TF dot ones like sentence 2, input type IDS equals TF dot concat, type CLS, comma, type S1, comma, type S2, axis equals -1 to tensor. And then inputs equals input word IDS, and this is a dictionary. Input word IDS to tensor. Input mask is input mask, and input type IDS is input type IDS, and it returns your inputs. So now what we're going to do is we're going to set up what data we're going to actually put into the encoder. Train input equals BERT underscore encode, train.anchor.values, comma, train.target.values, comma, tokenizer. And now what we're going to do is we're going to define our model, and it's defining the model is what I was not able to do. It went into error when I tried to define the model, and the reason why is because AutoModel is for AutoModel is for PyTorch, and TFAutoModel is for TensorFlow, but I don't have the web address to actually import the TFAutoModel. I wish I did. If I had the web address to do that, I would do it. So def build model, and BERT encoder equals TFAutoModel dot from pre-trained model path or name. Input word IDS equals TF.keras.input. Shape equals none. dtype equals TF.int64. Name equals input word IDS. Input mask equals TF.keras.input. Shape equals none, comma, df type equals TF.int64, comma, name equals input mask. Input type IDS equals TF.keras input, bracket, shape equals none, dtype equals TF.int64, name equals input type IDS. Embedding equals BERT encoder, brackets, input word IDS, comma, input mask, comma, input type IDS, and then 0. And that is where the model went into error because it said it would not accept a list. So that's why I can't put this online. Output equals tf.keras.layers.dense. Num class is what we previously defined, but it's going to be 5. Activation is softmax. Embedding is brackets, colon, comma, 0, comma, colon. Model equals tf.keras.model. Inputs equals input word IDS, input mask, input type IDS, outputs equals output. Model.compile, tf.keras.optimizer.atom. Learning rate equals 1e -5, comma, loss equals sparse categorical cross entropy, comma, metrics equals accuracy, and then we return the model. So now model equals build model, and then model summary. So now this is a summary of the model. And so now what we're going to do is we're just going to create a graph of the model, keras.utils.plot model, model statement classifier PNG. So there you go, there's the graph of it. And now we're going to create another graph, keras.utils.plot model. It's going to be model statement classifier with shape info.png. And so there you go, there's another graph. So now we're going to train the model. I'm only training it on 2 epochs because it takes so long to do it. Model.fit in train input, comma, train score dot values, comma, epochs equals 2, verbose equals 1, batch size equals 64, validation split equals 0.1. Now, I probably could increase the batch size and that would make it easier or quicker for the model to be trained, because the batch size was initially 16 and I increased it to 64 just to try to speed it up a little bit. So I might increase it a little bit, like make it 1028, and then like correct some of these other things in the Jupyter notebook just to make it a little bit tidier. And now we're going to make the predictions. Test input equals BERT encode, test.anchor values, comma, test.target values, comma, tokenizer. And then now we do the predictions. So predictions equals np.argmax for I in model.predict test input. Predictions equals le.inverse transform predictions. So you can see that early on in the program we used the label encoder, and now at the end of the program we have to reverse what we had done previously. So predictions equals np.array predictions, predictions equals np.ndArray flatten predictions, and then you got your predictions. So what I did was I used Seaborn to make a graph or a disk plot of the predictions, so you can see that you've got a lot of them on 0.25 and not very many on 1. And so now what we do is we prepare our submission. Submission prediction equals predictions. Submission.toCSV is submission CSV, comma, index equals false. Submission equals PD read CSV, submission CSV, and this is your submission. And that is what we would submit to Kaggle if we could, but unfortunately I can't submit it to Kaggle, and I told you before why I couldn't do that. So I'm going to go ahead and close this code review because we've covered the code already. If you like my code review, please like, subscribe, and share. I would like to thank all of my subscribers for supporting my channel. If you like my video, please like, subscribe, and share. And if you want to receive notifications whenever I make a video, please tap the bell button beside the subscribe button, and then you will be notified whenever I make a video. And thank you so much for watching my video. I look forward to making more code reviews for you in the future.